Good afternoon, everybody, and a warm welcome to our Creo 7 introduction webinar. In fact, this is our third webinar of this afternoon, in which we will guide you through some exciting new stuff within Creo 7. I would like to start this webinar by explaining a bit the environment. So we are in the GoToWebinar environment, and everybody can see a menu in which they can, let's say, coordinate their audio, but more importantly, a question box is available in which you can ask your questions. We will come back to the questions at the end of the webinar, and in fact, that due to the limit of time, we will not answer your specific question. We will come back to you on a personal notice after the webinar. We've put everybody on mute so that there will be no disruptions of noise coming from microphones, since we have a lot of attendees. And we would like to inform you that this webinar will be recorded for replay purposes on our website and on our YouTube channel. Okay, the agenda for this webinar. I will start briefly with an introduction of Creo 7, a general introduction. And then my colleague Martijn de Wet will take over and guide you through the new exciting stuff around Creo Generative Topology Optimisation, as you can see here, with an overview, some capabilities, a demonstration, and some future enhancements, which can be expected after Creo 7. Let me first introduce our team. As many of you know, Catcorn and GPO Solutions joined forces in 2017, and in that time we were a company of roughly 22, 23 people. So nowadays, 3 years later, we have grown very fast, and we are with an organization of 47 people, supporting companies in discrete manufacturing from early design until serviced and manufactured product. And we do that with, let's say, our consultant, high-level consultant expertise of our consultant team, and with our proven approach as a solution partner. You can also see a third company name on the slide, Infinite Simulation System. Infinite joined us at the beginning of this year as our dedicated team supporting the high-end simulation solutions of the ANSYS solution suite, in which we can support customers with mechanical, fluent, electronical, or all other kinds of simulation solutions. And we are proud to be, let's say, an elite partner and a preferred partner for as well as PTC as for ANSYS. Coming to the topic of today, the introduction of Creo 7. Creo 7 is stated by PTC that the design tool for the future, so the future of how you will design. And why is that the case? We see that our companies within discrete manufacturing are facing some specific challenges. First of all, there is an increasingly global competition. And with global competition, it's easier and easier for competitive disruption or new disruptive technologies to approach the market and to get market share. With that said, it's also the fact that the productivity within these companies is still growing, but the pace of growth of productivity is slowing down. So our customers are looking for new ways to increase their productivity. And one of the new ways of increasing productivity is embracing new and emerging technologies. And what's very important is that we see that there are emerging technologies coming, and that's not only said by us or by PTC, but by market research companies like Deloitte, who are looking into the market and seeing what kind of new technologies will change the way how companies will design and manufacture products in the coming years. And some of these topics on the slides are already there for a while. For example, we are talking about 3D printing and additive manufacturing for a while, but the technology and the way in which that can be implemented is changing fast. We can also see topics like augmented reality or industrial IoT on the slides, which are topics that are on top of mind of many executives within our companies, within our customer base, and they are thinking how they can embrace these new technologies and making them future-proof, the company's future-proof by implementing new technologies and implementing new business models. We are today going to talk about, in this session, about generative design, which you can see on the slides under the artificial intelligence, let's say, technology. And what PTC is doing with Creo 7 is two things. They are, as always, focusing on productivity enhancements within, let's say, the core Creo 7 functionality. And the second big thing is that they are focusing on these new emerging technologies, because if we can provide our customers with the best solutions in these areas, the areas for the future, you can make the difference in designing and manufacturing your product. So the specific technologies on which PTC is focusing are addressed on the slides. We just have had our webinar regarding real-time simulation. We have spoken to a lot of companies about IoT-driven design, and what we mean with that is that you can replace assumptions on how your products are behaving in the field with real-time data on how your products are behaving in the field. We see a lot of new interest in, let's say, augmented reality and also in design for additive manufacturing. And if you would need to, let's say, summarize Creo 7 and explain what the big thing in this release is, again, two things: productivity enhancement, which will make the daily work of an engineer easier and easier by implementing changes in the user interface and changes to, let's say, daily use functionality. And the four topics here on the slides, as discussed. And this is for me the perfect moment to hand over to Martijn de Wet, who will guide you towards all new exciting technologies and innovations on generative design. Martijn, the floor is yours.
Thank you, Robin, and good afternoon, everybody. Let's first have a look at the overview of what generative topology optimization is exactly. It is a new topology optimization tool based on the powerful FRUSTUM technology that essentially allows engineers to generate innovative designs or products based on predefined functional objectives, boundary condition loads, and specific manufacturing processes. Similarly to other topology optimization tools, you will start with the normal envelope shape, and then you define your, let's say, constraints, your conditions, and then the smart artificially driven generative design solver will go and generate your design based on your constraints. Once these constraints or your model is optimized for your conditions, you then have the ability to go and reconstruct it in a completely manufacturable model, so a BREP model, which is very important. Now, this is a very quick slide, so I'll go into the capabilities in a little bit more detail. Before I do that, I'd like to just quickly tell you that for Creo 7, we have the structural capabilities already available, and there is plans, of course, to introduce the thermal and modal capabilities in version 7.0.20. Now let's look at the capabilities in a little bit more detail. So first and foremost, as I've mentioned, we make use of the powerful FRUSTUM technologies to be able to make solve the analyses. This, coupled with the fact that the generative design application is completely integrated within Creo Parametric, gives designers full flexibility and enables them to rapidly make changes, update the designs, and generate optimized designs or products. As with other tools, the user interface is very uniform, so you'll also have a generative tree on the left-hand side. This allows you to quickly modify and edit existing simulation definition. For example, maybe you want to optimize slightly differently, and you can quickly access the controls from the left-hand side. One thing that's also very important is that you are able to set up multiple conditions on a model. The one that's very interesting is load cases, so you can apply many or a couple of load cases onto the same model. It will then consider all these load cases when it's performing its optimizations, giving you or yielding the proper results or outputted model. The same accounts for design criteria. You can set up multiple different design criteria, perhaps for one for 3D printing, one for milling, for example, and output multiple models. The last part on here is probably the most important one, because once you have your optimized results, what do you do with it? Well, you might want to go 3D print it, you might want to go mill it, for example, and we are able to automatically reconstruct a BREP model or a manufacturable model if you want, making the model essentially ready for downstream manufacturing processes such as 3D printing and milling, for example. I'll show you that in a little bit more detail, but let's start right in the beginning at what you can expect. So the first bit is making use of multi-body. Again, which is very interesting, you're able to use what we call design spaces to quickly define what volume or body should be optimized. So the area wherein the optimization engine will perform its work. You can also preserve geometry. So that is the stuff that should not be altered or changed, typically where your boundary conditions will be defined onto. And then another one is excluded geometry. So you can define exclude geometry and the solver will work around these volumes, essentially to act as obstacles, and that allows you to get a better outputted result. Of course, then you've defined your design spaces. Next thing would be your boundary conditions, your loads. And for example, you can define contact between bodies so that they are acting as bonded. Then is your design criteria. So the first one is optimization goals. You can see in this case, you'll see a limit volume or volume limit of 50%. Now this is how it is in Creo 7.000, but in the future PTC will be adding additional design goals. We also have different manufacturing and geometry constraints. So if we look at the manufacturing constraints as a start, the top one is build direction. That is for optimized for 3D printing, so to have less supporting structures. You can also optimize for molding with the parting line function, or perhaps you want to mold the parts. You can use the linear extrude function to define your constraints. Then you have geometric constraints as well. So maybe you want to make a symmetric part. You can select a symmetry plane to force this condition. And you, as a last option, also can control how uniform the material should be spreading when it generates the geometry, essentially. The last bit is just materials. So you can experiment with materials as well. Perhaps you want to do optimization for aluminium, maybe one for steel, and you can then set up multiple design criteria. Once your optimization is complete, you're able to also look at the integrity of the model. So if you look at the structural side, you can look at the deformations and the von Mises. You also have a similar legend that you have in Simulate Live. So easily to edit, easy to change. You have the maximum, minimum. You can edit the values of the minimum and the maximum. You can change between the different load cases. Maybe you want to review load case 1, load case 2 independently. That can definitely be done. And of course, maybe you want to animate it to see if your optimized design is performing as you would expect it to perform. Let's say you're happy with your results and your optimized geometry. The next step would be to output the results thereof. And what I mean by this is to generate your final model. Now, you can either do this as a new part, or you can make the optimizations in your own part. So the new part one is very interesting for use cases where you might have set up a master model and you want to output many variants from that one master model. And of course, the existing one could be that you've got the one model and you want to just optimize therein. There's two types of exports, if you will, or reconstructions you can apply. One is tessellated, so that's just keeping it faceted. Interesting if you're just interested in having a space claim to see if it will fit in nicely. And then of course, the interesting one is reconstructing to a BREP model, a manufacturing model, if you will. And then you have additional options such as the level of detail, how fine it should be. And if you do export it to a new part, you also have the ability to include or exclude the model tree. So perhaps you want to protect your IP, you just want to output the geometry for a supplier to make it to print it, for example, you can also do this. The outputted part will look something like this. And in this case, you will see the full structure, the full model tree. So maybe I want to make some edits afterwards and re-optimize. I can do this. I also have a generative design feature in my model tree. This is interesting because you are able to go back into your optimization study. You can change and update your criteria, your loads, constraints, and recreate essentially your constructive geometry. The last bit you see in the model tree will be the actual reconstruction. This is nicely grouped in your model tree and is also assigned into a multi-body, so it's easy to perform additional multi-body operations or Boolean operations once you've completed your optimization. That brings me to the demonstration. I'm going to do kind of the same model, so I'll start with an envelope. I'll define some volumes, some bodies, and we will go then and output some optimization results, have a look at how this is performing, and once we are happy with how this is performing, we will go and create a BREP model. In addition to this, I will show you some other output models and how they might look. So we'll start with what you see right here, and right at the beginning, I will go and create a new body. And what I'll do with this body is I'll call it the preservation body. So I want to keep all the geometry that should be reserved in this one. It's automatically activated for me, so all I need to do is go and create my volume. I'm going to use some of the existing Creo tools here to quickly offset some curves. And then we'll do the same for the internal curves just to project them. And once that's done, you can see I've got a normal extrude, but I can just simply drag it up into the top surface and have my first volume. I'm going to repeat the process for the bottom, and this time we'll just use 2 circles. So here we go. That's the first one, something like that. And it'll be the same diameter. Again, very quickly creating my needed volumes. So you can see on the left-hand side, I've got the new preservation volume, which contains these 2 extrude features. Now I'll go to the application, and you can see it's completely integrated, so I can easily switch between the application and my Creo environment. Once I start this, the first thing you'll notice is I've got all these indications on the left-hand side. Essentially, it's a guide to tell me how I should be defining or what I should define for my optimization study. I'll start with the design spaces, and here I've got the buttons. So my starting geometry, the geometry to be optimized. I simply select the body, and you can see it will change the display style for me. Same with preserved bodies. I can select one or multiple bodies to do this, and the color coding will be applied there as well. Now, for excluding, we've hidden the body. You can see the body running right to the middle of the model. I'm going to go and exclude this body as well, and you'll see as soon as we start the optimizations in just a bit that it will grow or generate the geometry right around here. So let me just hide it for now. The next thing I'd like to do is go over to the physics. You can see it's the next bit right here. We can go and apply constraints. Simply clicking on them, I'll just fix those. And we've modeled some shaft bodies that act as pins, if you will. We can apply the loads either directly to these, or we can apply them to the preserved bodies if we wish to do so. In this case, I'm applying them to the shafts. And of course, it can detect that these shafts aren't necessarily connected to the environment or the envelope. So I've got this contact button that allows me to connect these 2 together. So it acts as a bonded interface. I'm going to repeat the same loading condition, but just inverted or symmetrically in a different direction. And again, we will apply contact between these bodies. Now the last step to do is technically design criteria, but what I'll do is add an additional load case. So to make it a bit more complex, so I added this additional load case, and you can see in my structure tree, I've got structure 1, that's my first load case, and I've got structure 2 in my second load case. Of course, I can go and rename these to make more sense if I wish to do so. I'm going to fix the same surface, and this time we'll add the loading to the bottom surface right there. We'll do in the Y direction 3,500 newtons. With these conditions applied, I'm going to go and click on criteria, and here you can see I'm able to define a specific volume limit. So I want to keep 30% of the current envelope volume. I can also go and apply constraints. So for printing optimization, for molding, for milling. In this case, I'm going to keep it simple, and I'm simply going to apply a geometric constraint. I wanted to make the geometry symmetric around this symmetry plane. Last step is simply selecting a material. It's a very simple optimization will run now. With this done, I don't see any warnings on the left-hand side, so I know that I'm ready to optimize. I'm going to quickly show you the settings, so you can go for higher fidelity or lower fidelity, depending on what you want to achieve. You can control the element size, iterations, and stuff like that. I'm going to click Optimize here on Generate, and this could take about 2 minutes on my computer. Essentially, what it'll do is look at the boundary conditions I've defined, look at the preserved starting geometry, work therein, and then very importantly, apply both load cases and then apply the manufacturing constraint, or in this case, the geometric constraint I have decided for. You can see some geometry appearing, and what this will look like is almost as if it's trying to connect the two separate volumes together to make a rigid body. If we zoom in a little bit, you can see some of the geometry extending. This will most likely flare out and eventually connect to the right-hand side, and the same for the left-hand side. What I can show you already as well is if you look at the excluded material, you'll see how it's exactly optimizing around this volume. So I can use this volume to cordon off or to as an obstacle to avoid. Now at the bottom, you might see another piece coming through. And you can also keep track of the steps. So maybe it's important to talk about is optimizing steps. I've decided for 256 steps. It does not necessarily have to use 256 steps. It uses as much steps as it needs to go and reach a result. You typically, in this case, you might see something around 130, 140 steps. Can also keep track of my definition, so my element size, the amount of elements, and the weight. So I defined 30% volume, and I can see how this will vary. Now, of course, it's pretty stable, but in the beginning, it might vary quite significantly. If I look at the model again, this probably is just smoothing. So you can see in this area right here, it was quite a sharp edge, if you will call it a sharp edge. It's just smoothing out this bit, and then it is going to smooth out these contours to make a nice uniform geometry. You can control that with the spreading option as well. You can see it's almost done. It's just refining a little bit more, and then we can have a look at the results thereof. So step 114. Let me just give it some time to finish. Okay, so it's done. I can review it as just optimized geometry, but I also have the ability to look at its structural integrity in this case. So when I click on this button, you'll see it is looking at the structure 2 load case. It's looking at the von Mises stresses in Pascal. Maybe I'll just make it MPa in this case. Let's look at where the maximum minimum is. Perhaps I'll look at structure 1, where the maximum minimum is. And of course, we can also look at the displacement. So if I look at the displacement, maybe I'm interested in seeing it deform. So I'm going to start the animation tool, and we can then decide for this load case to animate it. So I can maybe increase the scale and the speed slightly. I'll press on the play button, and then you can have a look if your model is reacting the way you expect it under the specific loading condition. If we have a close look, you can see how the geometry is nicely connected to the preserved geometry, and it is behaving in a predictive manner. Now, let's say I'm happy with this result. I have the ability then to go and generate or output a BREP model. You could do one or two things. I can do the optimized BREP geometry inside of this part, or I can make a new part. I'm going to make a new part. Let's call it a variant. I'm going to try and use the BREP, and you can see as I've selected a new part, a BREP, I can select the detail I want, and I can also only output optimized geometry. So not the whole model tree you see on the left-hand side, but only a blob, if you will. I'm going to keep all the settings as is. I'm going to click on generate. I then have the ability to go and save this model. Let's just call it variant 1. Click OK. And in the background, essentially, it will go then and start generating this model. First and foremost, copying the bodies, copying the model tree of the original model as these initialization steps. Eventually, it'll go and create curves and make use of some surfacing functionality to connect to those curves. You shall see you're creating freestyle shapes. So the optimized geometry that it's creating is putting over a sort of faceted mesh, and then it's connecting to the curves that it created that are connected to the volumes you see at the back and of course the front. Now, technically speaking, this is a freestyle feature. So if you really want to, you can go and manipulate the freestyle feature afterwards. But in general, the results are quite smoothed out and nice. So this is not a required step. It's going to give it a little bit of time to finish. You should see when it jumps to step 4, it should almost be ready. And we'll have a model tree, we'll have a generative design feature. We'll also have the reconstructed geometry as a group as well as a body in the model tree. Okay, there we go. And I'm just going to change the display style a little bit. So what do you see on the left hand side? Of course, you've got all the bodies, you've got your original model tree, you've got a dedicated generative design feature. So you can go and edit again. Perhaps you want to make a change to your criteria, for example. And you see the reconstructed geometry, that is the piece between the preserved volumes as a group of features. And you see that as a body. This makes stuff like Boolean operations very easy. Maybe you want to subtract or merge additional things together, and you can do that. Now, what if I want to make a change? I've got two options. I can go back to my, let's say, master model, or because I have decided to import or contain or keep this model tree, I can go make a change directly in my variant. So I'm going to go and do that. And what I'll do is make quite a harsh change. We'll just change the excluded volume or the obstacle volume in my model. So immediately you'll see, and let me just show you that volume that has changed. What we'll see is an update in the notification center that, yeah, your design has changed significantly, so you have to rerun your optimization. All I really have to do is click on edit. Here you can see the volume still retains, and I can click on optimize. So I'm just going to run it again. Similar process will also take about 2 minutes to complete. In this case, you should see the optimized geometry build around this volume. So you can already see that a little bit, but let me maybe hide it. You can see how it's building around it. You'll see something very similar where it's again connecting on one side of the volume. By the way, you can see the old curves here that will be replaced in just a bit. Again, now we're moving to this side. It should connect soon. And I'm doing this on my computer as well, so there's no farm running in the background. All is quite powerful and quite efficient. So we can see the connection there. And again, you can see how it's moving around that volume right there. I'm going to give it a second or two to finish. And then what we'll do is we'll make a BREP model again. And then you can see how the structure looks. Basically, maybe I should do this for you guys so you can see the model tree. If I recall correctly, it will go and split these two up. So to create another hole in there, create another leg that will go and connect to this body. So it's trying to reduce the mass at the moment. You can see it's gone down from 0.2 kilograms. So it's rounded, of course, to 0.1. So it's more fine tuning based on my specific criteria. It's the same criteria, and that is just a volume constraint of 30% and then a geometric constraint around down the middle for symmetry. Okay. Most likely it will smooth out those connections. You can see it's already on step 130, so we should expect a result very soon. Yeah. Almost there. All right. It's completed. I'm not going to look at the results just yet. What I'll do is quickly go and generate the parts. I'll keep the same one. So we want to update the reconstructed geometry. I'll just generate. It will automatically detect that there's an existing reconstruction available for me. The first step will go and remove that model or the reconstruction for me and then initialize it again. So again, the curves, the volumes, you can actually see it happening in the background now. You can see the volume around the side of the surface. You can see the curves have already been created. The freestyle features have been connected essentially by means of these curves to the preserved volumes. A very similar process to the previous one. Once that all is complete, then it will go and do a solidification and neatly group everything into my model tree. So I'm just going to give it a second again to complete the reconstruction. We can review the model, and then we'll also look at some other alternatives. All right, similar, but now with my updated excluded volume. And again, I have the same reconstructed geometry, and I've got the feature to edit my optimizations if I wish to do so. Now, one other thing you could do, and let me show you this, is I'll do this really quickly. You can create additional design criteria. You can see I'm creating a new one now. And I want to quickly show you how you could, for example, have the part optimized for milling. So I'll give it a draft of 3 degrees. We'll go and apply symmetry, and we'll add the same material. So all I did really is add this extrude direction constraint, and I'll optimize. I'm not going to have it complete. I'm just going to show you how it builds this, and then I'll show you the complete model just in the interest of time. Interesting here is how you can see how it immediately applies that draft to my volumes. And once it starts connecting the volumes, you can see it's always with respect to that specific manufacturing condition. So it'll retain the draft angle to make sure that it can be milled. Look at the bottom, you can see this hard edge forming, and then obviously that tapers up to the top with the geometry. And again, very similar to the other one, you'll see how it's trying to connect these volumes together. So I think I'll stop it in just a second, and what I'll do is show you the completed results. So I've opened it already here. This is how it looks. So eventually you'll see extra beams being created and extra support going on there. And I took the liberty of also perhaps creating an additional one. This is one optimized for 3D printing with a specific critical build angle. You can see it right there. And that concludes my demonstration. I'd like to quickly go back to the slide and just quickly show you what we can expect in the future. So Creo 7020. Essentially, PTC is planning to introduce cloud-based technology. The idea being that you can upload your study, so all your different design criteria, your load cases, your model, you can upload it. The cloud environment can then perform your simulations for you, so you don't have to use your own computer or the computational power of your own computer. These can then be previewed essentially inside the cloud environment. You can compare them by means of a graph, by means of specific criteria, so load cases, manufacturing methods, materials, maybe the stresses, for example. You can even see and compare the actual structure integrity, for example. So what is the deformation? What does the stresses look like? Once that's done, you're able to download the model back into Creo as a tessellated model, and you can perform the reconstruction as required from there. And of course, what is the idea? One central dashboard where you can view all your optimizations, run them, compare them, output them as needed. So what I did is I quickly added a small video teaser to show you how this will look, kind of like the slides, and you'll see an example model in the cloud environment. The first bit is the comparison between the variants. You can see the graph, you select them, they're highlighted in the graph. You can then filter by material, which is done in this case. So picking 3 materials to then compare. From there, a sub-selection has been made of, say, 3 designs. So you just fine-tuning which designs is optimal for you, and the structural integrity of these few components are being looked at. So you can see at the bottom there what material, what safety factor, the mass, the volume, the stresses, the displacement, as well as then getting a fringe plot to see how the model will behave as well. When this is done, you can just output the model back into Creo and then perform your outputted B-rep geometry. That concludes the part of the demonstration. So we'll start at the questions and answers section. Let me just quickly open that. 1 second, please. Okay. So the first question we have, how would this model look if I optimized for casting? Could you change this afterwards as an option inside the generative feature? So I think the best thing to do is maybe take up contact with you and look at what it would look like with one of your models. I could see if that is something you would want to look at. We don't really have time to optimize one more model yet, unfortunately. But the second bit to your question is, yes, you can then edit the generative feature afterwards. So you can optimize forecasting, sure, and then you're able to edit the results or the optimized study afterwards. I think we'll take up contact with you to see how we can show how this will look. Then, can you add features to the generated geometry? Technically speaking, it's possible. It's a solidified feature. So if you want to go and add extra geometry, you can drill holes, you can add blends to it. Third question we have is, what type of license do I need for this? So you need a generative topology optimization license, and this is available as well as a locked license as an extension, as well as a floating option. Okay, let me just see if there are any additional questions. I don't see any, so maybe what I'll do is I'm going to hand over to Robin to conclude the webinar series. Thank you for your time, and thank you for listening and joining, and hope you saw some interesting stuff. Thank you.
Yeah,
Robin?
yeah, Martijn, thank you for your clear explanation and interesting presentation and demonstration. And then to all attendees, we would like to thank you for your attendance. Maybe you have seen only this this webinar. If that's the case, we have had 2 more webinars in this series this afternoon. All these webinars will be available on our website and on our YouTube channel, the Cat Corner GPO Solutions YouTube channel. Please reach out to us whenever you have questions around Creo 7 or implementing Creo 7 or on specific solutions which we have shown today. And from my side, I would like to thank you again for your attendance. Have a good day, and hopefully we can work with you on implementing Creo 7 on short term. Thank you, and see you next time. Bye-bye.